You ever wondered why it rains or why the wind blows? Well, that's because nature, weather in particular, is in a dynamic equilibrium. It's one of the most important concepts that reaches over and covers all areas of science. Today we're going to begin to try to understand just a little bit of what a dynamic equilibrium is and understand something of the Chateliers principle, which describes the way dynamic equilibriums work. All right, dynamic equilibrium. Now when you first hear these two words, if you know what those words mean, that should seem confusing, because this word means movement and this word means balance, okay, in its simplest conceptual form. How can you have movement and also have balance? Okay, well, a lot of things that are in a balance in nature, the balance doesn't change, but underlying that, the stuff that you really don't see so much is actually moving. Okay, in nature we have a balance between the number of mice and the number of snakes. Okay, and the snakes eat the mice eat whatever food is available out there, you know, and things like that. If the number of mice gets smaller, what happens to the number of snakes? They get smaller, okay? And so this equilibrium balances back out again. So the balance between the number of mice and the snakes is here. If you do something to cause a change in that balance, like the mice go down, the number of snakes go down, okay? Also, if you increase the number of snakes, they eat more mice, right? And then the snakes go down. So it's going to balance out one way or the other. That makes sense? Now that's in nature, of course, and we're dealing with chemistry is in nature too, but we don't often talk about mice and snakes when we talk about chemistry. We talk about other things that have to do with that kind of balance, and since we're in a thermochemistry unit, let's talk about things that have to do with thermochemistry, okay? So let's take a look at maybe a container here. And in that container, I'm going to put some water. And let's seal up the top of our container. I'm going to put a cap on it. All right, I just put a cap on the top of that container. Got it? Now, we all know that water evaporates. Yes? If you take a cup of water and put it on your kitchen counter, in a week or so, that water's going to be gone because it evaporates. All right? But if we seal up the top of that cup, the water won't evaporate. At least not all of it will. What happens is some of the water molecules, in this sample of water, you've got some fast-moving water molecules, some slow-moving water molecules, okay? And the average of all the movements give us the temperature. Okay, so when we talk about temperature being a measure of the average random momentum of particles in a substance, that's what we mean. That some are going to be moving fast and some are moving slow, but the average is what we get the temperature from. So some of those molecules are moving fast enough to want to escape and become like steam. Now, if the water is less than 100 degrees, the boiling point of water, then we don't call it a gas when it escapes into this gaseous form. We call it a vapor. Okay? So the terms are somewhat different. Okay? They're applied differently. Gas means the temperature is above 100 degrees. Vapor means the temperature is below 100 degrees. Okay? And you can have water vapor even at below 0 degrees C. Okay? Things, if you ever noticed in the freezer, you have ice cubes in there for a long time, they seem to shrink, because some of those water molecules are actually escaping into a gaseous form from the surface of the water molecules. Okay? Well, if we cap the top of this container, then the water molecules that are escaping can't escape the container. There are also water molecules that are returning back to the liquid state. They're slowing down, hitting the top of the liquid, and rejoining the liquid. So there's a constant movement of water escaping the liquid and becoming gas or vapor, and water returning back to the liquid state. Okay? If we seal it up, there is a point where the rate or number of water molecules becoming gas or vapor will equal the number of water molecules becoming liquid. And that's called an equilibrium. At that point, we have constant change, dynamic, but an equilibrium because the number of water molecules up here doesn't change. Does that make sense?
Yeah.
Question: what happens if I heat it up? Now, I just put this on a hot plate and heat it up a little bit. Before it boils, we're not boiling, we're just warming it up some. Is anything going to change? If you get it hot enough, it'll bubble, which means it's boiling. But we're not going to heat it up that much. We're just going to make it warmer. Okay? Huh? It wants to evaporate more, doesn't it? So, by heating up this system, increasing the temperature goes up, we shift the equilibrium. Now, what I mean by shift the equilibrium, it wants to vaporize more water molecules. The result is that there's a higher percentage of water molecules up here in the gaseous phase. Okay, the vapor phase.
What's that last word?
Equilibrium. Equilibrium. Okay, shifts the equilibrium. So that there's a new balance point established. We keep moving more water molecules in that vapor state until the rate at which the vapor, the liquids crossing that boundary between liquid and gas, increase until the rate at which they are returning back to the liquid is equal again. Okay, it's equal out. Reaches a new equilibrium. So what happens is we've created something. We've changed the conditions that change the point of equilibrium. We've changed the balance point, but eventually we reach a new balance point. Okay, you with me?
Yeah.
Okay. Now that idea, that concept, that equilibriums can be changed and a new equilibrium established is the basic idea behind something called the Le Chatelier principle. Okay, it's named for this guy here, Le Chatelier. All right, so it's called the Le Chatelier principle. I'm just giving you his name. Let you see his face. Okay, you can look up more about him later if you want to. Okay, just showing that's what it is.
What are you doing again?
He's the one that figured out this behavior and described this. Okay, and so the way that he would have described it might be a little bit confusing to you guys. And what he described is that when there's a dynamic equilibrium, and you do something that changes the conditions for that equilibrium. When you have a dynamic equilibrium and you do something to change the conditions for that equilibrium, then the dynamic equilibrium point, the point of balance between whatever two parts there are, will establish a new equilibrium. That makes sense? Or new point of equilibrium. The equilibrium always exists. It's a point of equilibrium we're talking about here. The amount of, in this case, water vapor in the air. Okay? Now the equilibrium is the balance. In this case, the balance between those water molecules that are liquid and those water molecules that are vapor. Okay?
Can you say one more time, please?
The Le Chatelier principle, in a super simplified sort of way, is saying that when you have a dynamic equilibrium, and there are lots of dynamic equilibriums. This is just one kind. Okay? The rats and mice thing, or the mice and snakes thing is an equilibrium, just the same. But he described it, when you have a dynamic equilibrium and something causes a shift or something affects that equilibrium. You have a dynamic equilibrium and something affects that equilibrium. He called it a pressure, but I don't want to use pressure because that might confuse you with air pressure. Okay, when you cause something to affect that equilibrium, then the equilibrium will simply shift to a new point of equilibrium. Now, some of these equilibrium points you guys are familiar with in chemistry. For an example, if I have some sugar that I want to dissolve in a glass of tea, how many of you ever tried to dissolve sugar in a glass of tea? Not many people try to dissolve sugar in a glass of tea?
Cold tea or hot tea?
Let's start with cold tea.
Okay, yeah.
Kind of hard, isn't it? Pretty, huh? You have to stir and stir and stir and stir and stir, right? And if you put too much in there, you're still going to have some falling on the bottom, aren't you? How can you get that all that sugar to dissolve in the tea?
Heat it up.
Heat it up. So dissolving of certain solids, you can change the point of equilibrium by heating it up. Just by heating it up. All right. Now, sugar and water are kind of unusual. They form, I think it's called an azeotrope. At a certain point, around 65 or so degrees C, I believe it is, sugar and water start to form a new kind of bond together, and you make a syrup. So you can cool it back down, it never comes back apart again.
That's cool.
Yeah, so that's what a syrup is, basically. Okay. But most solids, you don't actually get that behavior. All right. Now, we haven't looked at it that way, but that brings us kind of back to our ice cream lab. So let's look at liquids and solids together. Okay. So in our ice cream lab, we're going to be freezing a liquid, right? That's part of our goal, is it not? That's what you want? Okay, C. All right. As in yes, and not the grade you want in the class. All right. So let's look at, now I'm going to do something that really doesn't happen because most of the time when you put ice cubes in water, they float. I said that a while ago. But I'm going to put my ice cube right here kind of in the middle just for this illustration, okay? I think I need to get a new marker. That one's about worn out. Well, it's not a crayon. It's a different kind of marker. Anyway, so you don't often think about it this way, but there is an actual equilibrium existing between this liquid here and this solid. Okay? If I have the temperature down at a freezing temperature of water, about 0 degrees C, there are water molecules along the surface of this ice cube that are wiggling fast enough that they will become part of the liquid. At the same time, there are water molecules in the water moving slow enough that they'll become part of the solid if they stick to it. Okay? Well, eventually, enough of the water molecules in the ice cube will leave and form a solid along the edge of the glass. And then eventually will start to grow across the top. So if I have this, say this is a cup or a beaker, and I have it in a perfectly controlled refrigerator where the temperature stays at 0 degrees C, eventually the ice cube disappears and the ice appears on the top. Does that make sense? Now what's going to happen when you're making ice cream, if you were to put just the water in there, you first get ice across the top and then it starts to move down as it gets more and more frozen. Okay? But along that surface there is still an equilibrium going on. Some molecules are becoming liquid, all the molecules are becoming solid all the time. So that equilibrium exists. It may not look like it, but that's what's happening. You can't see it happening because the molecules are too small to see, and we don't have devices that will allow us to see moving molecules like that. But we know it's happening by behavior. You know, we can look at other things and figure it out. Okay? Any questions about equilibrium and what it means? Any questions about the Le Chatelier principle and what it means? Because that's important. Look, if there is a single subject, there are actually two big subjects in high school science that reach across all areas of science and are important to every area of science. We don't see it so much in chemistry, one of them, and that's evolution, okay? But it does affect chemistry. But the one thing that reaches across all areas of science, this concept, is equilibrium and the Le Chatelier principle. Le Chatelier, okay? That's important. It's going to be important in biology or in physics, in earth science. You name the area of science, yes, even computer science, it's important.